All right, I just wanted to go through this moment of inertia, rotational inertia of a hoop. So if I have a particle here and a particle here, and we are rotating them about the center axis, and those particles are a distance r away from that rotational point. If we summed up all the mass at those distances, we would have 2m times r squared, because you have mr squared of the one to the left plus mr squared to the one to the right, so we would just get twice what it would be for one of them. If I add another down here, but also the distance r away from the center point, I'm going to show that. Since they're all rotating around here, going this way, we would just include that third mass. Mr squared plus mr squared plus mr squared equals 3mr squared, if they're all the same mass. If I add another one here, 4mr squared. If I add another one here, 5mr squared. 6, 7, 8, 9, 10, 11, 12, 13, 14, and infinite. Okay, so let's look at it this way. Instead of calling them a large particle of mass, we called it a very, very small particle of mass, so that we would have an infinite amount of those little particles lined up together, which would equal the total mass of that object, which would be a ring. And that ring would rotate about a center point here where there is no mass. So if you threw a hoop through the air, it would look as if the center of that hoop is stationary while the whole ring rotates around it. Stationary with respect to the other particles. This center of mass would move in a linear line or an arced pattern if we're having a projectile type of motion. The idea here is if we have a ring and each little section here is a very small piece of mass of the ring, every little piece of mass is at the same distance away. So looking at the integral form of this, since r is constant for every piece of mass, and it's the value of capital R on my diagram, I really can pull out the constant out of the integral, and I'm just summing up all the little pieces of mass, which would just be the total mass of the ring.